Welcome to the ET380 video for the Lab 4 Sine Wave Oscillator Lab. Right now, let's take a look at the free-running phase shift sine wave oscillator. Okay, here's our circuit in Multisim. Let's go ahead and add a oscilloscope. And we need to borrow one of the grounds. And let's go ahead and input this, start our simulation, recenter this, and open up our scope and see if we can get this guy to oscillate. And we do, and it looks good. So let's see here, what do we got here? So let's go to measure, and let's see what our frequency is. And let's see what our amplitude is. Let's go to peak. Okay, so it looks like we got 3.06 kilohertz and 28.2 volts peak to peak. And let's go ahead and do a single sequence. Looking good. Let's take a look. Okay, let's calculate the gain. We need to remove one side of our pot. And let's take a DMM. And see what kind of resistance we get. Start our simulator, and it's perfectly 500K. So if we take our 10K, our gain is 50. And it takes a gain greater than 31 in order for this to oscillate, and 50 is greater than 31, so we're good. Here's a close-up of our sine wave, and we come up with 3 kilohertz and 28 volts peak to peak. Here's our formula. And I've inserted our 10K and our capacitor size, and I come up with 2,953 hertz, which is very, very close to our 3K that we came up on our design, so that's good. Okay, we're back at our oscillator circuit. Let's go ahead and change our values here. I'm going to go ahead and let's go to label. I'm going to call that guy 1A. And let's turn off our simulation. And this guy's going to be R2A. And the reason I'm using A is it gets upset when I reuse the same number. So let's try R3A. Because we need to use our connection here, and this guy is going to be R4. See if that's used anywhere else. Okay, now let's take our scope, and we're going to go between 3 and 4. And let's restart our simulation and see what we get. Restart our, and let's start our blue. And let's see here, let's go ahead and go to 10 and see what we get. Nope, let's go to, there we go. And let's spread it out a little bit so we get a closer view. Okay, so let's go to a sequence, and that's our output. Okay, here's a close-up of our output of our oscilloscope in yellow, and blue would be our oscillation circuit, and same frequency, and we get a very, very large gain. Okay, let's take a look at our Wien bridge oscillator. Here's my oscillator circuit I built in Multisim. Let's go ahead and get a oscilloscope, borrow a ground, and let's check the output. Start our simulation, open up our scope, and it's oscillating. That is very good. So let's bring this down. There we go. Excellent. So we're oscillating. And so let's go ahead and go to measure and see what we got here. So let's go to frequency. A little over 1K. And let's go ahead and check our peak to peak. And we have 11.6. Good. Here's a close-up of our oscilloscope screen. And we have a frequency of 1.05 kilohertz and peak to peak of 11.6 volts. Okay, so let's replace our 0.01 microfarads with a 0.1. So let's just go to replace and see what happens here. So we're going to have to go to capacitor, and let's go to 0.1. That might be the simplest way to do it. Just go to replace. We can go ahead and change the number, but it seems to be bouncing around. Okay, that looks like all of them. So let's go ahead and start our simulation, open up our scope, run stopped, get it running again. Let's change our time. And it looks like we have 105 hertz. Very good. Okay, here's our calculation of 106. Here's our close-up of our oscilloscope screen. And we have 105. You can't get better than that. Okay, so we need to change another capacitor. So let's go ahead and shut down our simulation. Let's close out our scope. And we need to replace these two. So we're going to use go to replace, and we got a 0.47. And 0.47. So let's go to replace. 0.4 is good, it's already there. Let's start our simulation. Open up our scope. Let's get a few more. There we go. And good. So we have 22.4 hertz. That looks pretty good. Okay, here's my calculation of 22.5 and a close-up of our oscilloscope, 22.4. Can't beat that.